This next lesson is something that's going to be incredibly important for the rest of this course, which is the fact that reactions are actually reversible. Up until this point, we always think reactants go to products, reactants go to products. But in reality, reactions can go both ways. So reactions can form into products, but the products could also form into the reactants. And there's a lot of factors that determine which way it's going to go and kind of what's going to happen. And that's sort of some of the topics that we're going to be covering in the next few units. But for right now, we're just going to look at the difference in the activation energy and the enthalpy of forward and reverse reactions. So a forward reaction on a potential energy diagram has this left part as the reactants reaching the activated complex and then has your products on the right hand side. Your delta H, this one would be an exothermic reaction because it's a step down, and your activation energy forwards goes from reactants to activated complex. But in reality, this reaction could happen in reverse as well, where all of a sudden these are the reactants. So the products become your reactants. So the activation energy is the difference between the product line, which is now my reactant line, and the activated complex. But the delta H is still the same, but instead of being an exothermic reaction, it would be an endothermic reaction. So the first thing we're going to do is just practice like looking at a potential energy diagram and interpreting enthalpy, whether it's exothermic and endothermic, activation energy, and then the energy of the activated complex in both directions. So here I have a reaction, and we're going to look at it forwards, where this is my reactants and this is my products. The first thing I want to determine is my delta H. So my delta H is going to be the heat content of the products minus the heat content of the reactants. And so for this one, it's going to be 50 minus 25, which makes my delta H a positive 25 kilojoules. This is an endothermic reaction. Why? Because my delta H is positive and because it's a step up. There's an input in energy. The activation energy for this specific scenario is going to be from the reactants on the left up to the activated complex. So I'm going from 25 up to 125, which makes the activation energy 100 kilojoules. And the energy of the activated complex is 125 kilojoules. Whereas if I look at this in reverse, all of a sudden these would be my reactants and these would be my products. So the delta H, instead of being positive 25, would actually be negative 25. And if we calculate it, right, products minus reactants, this time my products is going to have 25 kilojoules of energy. My reactants have 50, and so I can see that it comes out as negative 25 kilojoules. This would be an exothermic reaction. And how can I tell? Well, my heat energy of my content came out negative, as well as it's a step down. The activation energy of this potential energy diagram is the difference between the reactants, which used to be the products. So it's going to be from 50 up to that energy of my activated complex, which is still 125. That doesn't change. But this time it's going to be an activation energy of 75 kilojoules, which is less. So my reverse reaction would actually be faster. And the energy of my activated complex does not change. So what really, like the biggest changes are the delta H remains the same from an absolute value standpoint, but in the forward reaction it'll be positive, and in the reverse reaction it'll be negative, right? So one of my reactions is endothermic, one of my reactions is exothermic, but my activation energy changes altogether, but my energy of my activated complex doesn't change at all, right? So there's things that change and there's things that don't change. And just to emphasize, there is this equation that you could use if they were asking you for missing pieces of information, which is that the activation energy forwards is equal to the activation energy in reverse plus the change in enthalpy. So if I looked at this, I would say that my activation energy forwards was 100 kilojoules. And the activation energy of the reverse reaction is 75, and then the enthalpy change is 25. So 100 is equal to the 75 plus the 25. And you can see that on the diagram. I find like this equation's awesome. This equation up here, I realize that you guys can't see my pointer when I point. But this equation up here is awesome, but I also feel like sometimes it's just easier to see it on the diagram, right? So if I have my activation energy of my forwards reaction going from reactants to activated complex, and then I know that my delta H is in here, then I know in a reverse direction that the 100 minus the 25 would leave me with that 75 kilojoules for my activation energy of my reverse reaction. Okay, so now pause the video, and I want you to give these two a go, and then we're going to do a couple more examples after this. So for this one, my enthalpy change is going to go from products to reactants. So this time it's going to be a step down. So my forward reaction, my delta H is going to be negative 50 kilojoules. And you notice I didn't do that with the equation. If you don't need the equation, you don't have to. If you wanted to use the equation, you'd go products minus reactants. So the heat energy of my products is at 25 kilojoules minus my heat energy of my reactants is at 75 kilojoules, which would give me negative 50 kilojoules. Is this an exothermic or an endothermic reaction? Well, this time my forward reaction is exothermic because it's a step down and my heat change is negative. My activation energy is from reactants to activated complex. My activation energy is going to go from 75 kilojoules up to 125, which is going to be 50 kilojoules. And again, my activated complex is 125, and this is the thing that's not going to change. Whereas if I look in reverse, all of a sudden it's a step up. So I'm having an input of energy, and my enthalpy change is going to be positive 50 kilojoules. Again, you can calculate that by doing heat of products minus heat of reactants, where this time my products are 75 and my reactants are 25, which would give me positive 50 kilojoules. This reaction is endothermic. And then my activation energy is going to go from reactants to top of bump, right? So this is going to be my activation energy. So I can see it visually on my graph that it's going from 25 up to 125. So it's going to be 100 kilojoules. But I also could have looked at it by saying that it's the activation of my forwards reaction plus my enthalpy change, which is going to be 100 kilojoules. And again, the energy of my activated complex doesn't change. Cool. So hopefully you're getting kind of a good feeling about this forwards and reverse thing. It's a bit of a mind warp when you first start doing it, but by the end of this course, you're going to think of every reaction as being able to go forwards and reverse. All right, so we are going to now look from scratch. It's going to say something like, draw and label the potential energy diagram to show the enthalpy change and activation energies, meaning forwards and reverse, for a reaction which reactants goes to products plus 20 kilojoules and activation energy in reverse is 165 kilojoules. So you have two choices. You can use your equation. Whoa, that is scrolling on its own. So the equation is that activation energy forwards is equal to activation energy in reverse plus delta H. So we could know that the activation energy in reverse is 165 kilojoules. And to that, we could add, now here's the question, do we add 20 or do we add negative 20? Since this is forwards, you are going to be looking at the fact that the forwards reaction is exothermic, so you would be adding negative 20. And so that would come out with an activation energy forwards of 145 kilojoules. I sometimes find that tricky. You know, it is, if you've taken a physics course or anything where you have to decide whether something's positive or negative, it's hard. So instead, I often will actually start with my diagram. So in my diagram, I've got my axes. On my y-axis, I have potential energy. And my x-axis, it's something like reaction pathway. I often shorten the word reaction to just RXN. So reaction pathway or reaction proceeds or even something like time would be great. But I know that my forwards reaction, because it's exothermic, is going to be a step down. So I'm just going to roughly sketch this with a step down. I'm going to label on here that I have a delta H in my forwards reaction of negative 20 kilojoules. And I know that my activation energy in reverse, is equal to 165 kilojoules. So from here, I could also tell that the forwards reaction, so that activation energy from reactants to products, sorry, this is going terribly slanted. Not too sure why, okay, is going to be the difference between the activation energy in reverse and the enthalpy change. And so it's going to be 165 minus 20, which is 145 kilojoules. So like I said, sometimes it's easier not to do a calculation, but to actually visually see the reaction. Oh, I cannot write a 4. 145 kilojoules. So do I have everything? So I wanted to draw and label a potential energy diagram to show the enthalpy change. Now I've shown the enthalpy change in reverse. If I wanted to show the enthalpy change, in forwards, if I wanted to show it in reverse, I would say that delta H is equal to positive 20 kilojoules. I often find in these diagrams, as long as you put delta H in one direction, usually the forwards direction, you're fine. And then it's just sort of interpreted for the reverse. And sometimes they'll actually do a dotted line across. What's important is that you include the activation energy forwards, activation energy reverse, and then the enthalpy change. And often, like I said, the enthalpy change of the forwards reaction. All right, let's try this next one. This next one is telling me that I have an enthalpy change of 81 kilojoules and the activation energy forwards of 256. And it's asking me what is the activation energy in reverse. Now for this one, I haven't said draw the potential energy diagram because I wanted to give you the option of just using the formula, but it's sort of up to you. But what I would look at is that if I was to draw the diagram, whoa, that is leggy, okay, that my forwards reaction is endothermic. So I'm going to draw it simply with a step up. So reactants up to activation energy, and then there's my products. And someone's going to nail me for not doing this to scale. Sorry. Not very good at it. Okay. I know that this difference, right? This is an enthalpy change of positive 81 kilojoules. And then this is an activation energy forwards of positive 256. When I say to scale, I'm not too sure if this 256 is in scale to 81. It's actually not too bad. It maybe should have been a little bit smaller. But again, as long as I'm showing an endothermic reaction and that my activation energy is higher than my products, obviously, I think I'm pretty good. So then if I wanted to find my activation energy in reverse, I know that my equation is activation energy forwards is equal to activation energy in reverse plus delta H. So if I wanted to find my activation energy in reverse, it would be my activation energy forwards minus my delta H. And so for this one, it's going to be 256 minus that 81. So since my forward reaction is endothermic, I'm subtracting positive 81, and I end up with 175 kilojoules. And then you just double check that makes sense, right? Should my activation energy in reverse be smaller than my activation energy forwards? Yeah, it should, right? Because it's an endothermic reaction. Whereas in an exothermic reaction, your activation energy in reverse is larger than your activation energy forwards. All right, if you're feeling pretty good with this, pause the video, give this one a go. Otherwise, just keep watching. So this one I have said, draw and label the potential energy diagram to show the enthalpy change and activation energies for a reaction in which my forward activation energy is 65 and my reverse activation is 15. So if we think about drawing this, again, we've got potential energy and we've got reaction pathway or proceeds or whatever you want to put on your x-axis. My activation energy forwards is larger than my activation energy in reverse. Now, if you're not sure what that means from a picture point of view, you could jump right to the formula. So again, activation energy forwards is equal to activation energy in reverse plus delta H. So if I wanted to solve for delta H, I would do activation energy forwards minus activation energy in reverse, which is going to be 65 minus 15, which is going to give me an enthalpy change of 50 kilojoules. Now this came out as positive, which means that it's going to be an endothermic reaction. Now, does that make sense? Well, I know that my bump from reactants to activated complex forwards has to be 65 kilojoules, right? So this activation energy forwards is 65 kilojoules. And then my activation energy in reverse is only 15. So it means that it had to be an endothermic reaction with an input of energy in a forwards direction. So my delta H is positive 50 kilojoules. Awesome. Hope you're feeling good. Go give these questions a go.